The PAF implicated atherosclerosis theory. Platelet activating factor PAF, a molecular link between atherosclerosis theories, from C.A. Demopoulos H.C. Karantonis S. Antonopoulou, published in the European Journal of Lipid Science and Technology in 2003. From the ancient times, people tried to find some relation between nutrition and diseases. Today, we know that at least 3 diseases are related to nutrition: obesity, diabetes type 2, and cardiovascular diseases. Another disease is cancer, where 30% of the cases may be due to nutrition. Although epidemiological studies over the past 50 years have revealed numerous risk factors for atherogenesis and atherosclerosis, pathomechanisms remain a subject of controversy. Atherosclerosis is a multifactorial process with a level of complexity that renders it difficult to clearly define the degree of importance of any one risk factor. On the other hand, it is well known that Mediterranean diet protects against atherogenesis, atherosclerosis, and cardiovascular diseases. We tried a new biochemical approach on the subject, and we proposed a mechanism which may help to explain the beneficial effects of the Mediterranean diet beyond statistical and epidemiological data. According to our theory, PAF is a crucial molecule for the initiation of atherosclerosis, and the beneficial effect of the Mediterranean diet are due to the existence of PAF antagonists in Mediterranean foods. The following mechanism we propose unifies the so far proposed theories of atherogenesis, combining our new experimental data with the existing experimental data of the scientific community. This is an artery with blood cells. Here are the endothelial cells, the smooth muscle cells, and the vessel wall. Leukocytes and platelets secrete the enzyme acetylhydrolase, which circulates in blood in LDL and HDL. LDL is oxidized, and during this oxidation, phospholipids, PL, are converted to PAF and PAF-like lipids. These active lipids are inactivated by acetylhydrolase, AH, producing lysopaf. PAF acetylhydrolase is progressively inactivated upon LDL oxidation, and thus LDL loses its ability to protect against the pro-inflammatory actions of PAF and PAF-like lipids. The role of antioxidants, as well as the role of acetylhydrolase in LDL and HDL, is revealed. At the same time, leukocytes and platelets are activated too. PAF and cytokines are produced, and adhesion molecules in blue, as well as their ligands in yellow, are translocated to the surface of the activated cells. LDL through PAF and PAF-like lipids can activate endothelial cells, leukocytes, and platelets. PAF antagonists can inhibit this action. When PAF levels increase irregularly because of the LDL oxidation or other pathological reasons, PAF binds to the endothelial receptors and activates these cells. Activated endothelial cells rapidly produce and display PAF molecules on their surfaces, inducing a positive feedback control. In addition, cytokines are released upon cell activation, and the process is amplified through positive feedback control too. Finally, adhesion molecules are rapidly translocated to the surface of the inflamed cell. The activation of endothelial cells is leading to a dysfunctional endothelium with increased permeability. The formation of dysfunctional endothelium is also the cause in other pathological conditions, such as glomerulonephritis in the kidneys, which is now called glomerulosclerosis, and the involvement of PAF has been proven. In addition, in COVID-19, which is a vascular disease, the formation of dysfunctional endothelium is the first stage for the observed multi-organ damage. when the involvement of PAF remains to be proven. Various factors that are released upon cell activation hemoattract blood cells on the endothelium and initiate atherosclerotic process. After platelet adhesion through fibrinogen, the cells are stabilized with collagen, von Willebrand factor, etc., and make, along with leukocytes, a layer on the dysfunctional endothelium. Leukocytes roll along the vascular endothelial cells or along the layer of platelets leukocytes. When leukocytes are bound to endothelial cell through adhesion molecule and PAF, then leukocytes arrest rolling and mediate firm adhesion between them and the endothelial wall. This is one more key role for PAF in atherosclerosis propagation. Rolling and adhesion of monocytes on activated endothelial cells are suppressed by omega-3 fatty acids by affecting endothelial PAF production. Leukocytes move into subendothelial space, migration, and monocytes differentiate into macrophages. Increased permeability of the dysfunctional endothelium permits large molecules such as oxidized LDLs to migrate to the subendothelium through cell junctions. Oxidized LDL undergoes irregular scavenger receptor-mediated uptaking by macrophages to form foam cells. LDL migrates also to the subendothelium, where the oxidative procedure is easier and the oxidized LDL is uptaken by the monocytes and new foam cells are produced. Several lines of evidence indicate that intramural retention of atherogenic lipoproteins which produce PAF involves extracellular matrix, proteoglycans and perhaps other structural elements, and lipolytic enzymes, lipoprotein lipase and sphingomyelinase. The above response to retention hypothesis enforces the role of PAF and of extracellular matrix too. Monocyte-derived macrophages and macrophage-derived foam cells synthesize PAF upon phagocytic activity stimulation. The initial signal from the circulating in the blood PAF, amplified from the macrophage and foam cells. PAF stimulates transcription of epidermal growth factor (EGF) in monocytes, and proliferation of smooth muscle cells takes place, leading to corrupted subendothelial architecture. As foam cells accumulate, the intimal thickness increases and fatty streak is formed, which is the earliest stage of atherosclerosis visible to the naked eye. Fatty streak is covered by a fibrous cap and contains foam cells, lymphocytes, monocytes, macrophages, proliferated smooth muscle cells, cellular fragments, calcium, and cholesterol. Phagocytic activation of foam cells results in PAF production in the fatty streak and advanced lesions. Within this localized lesion, continued inflammation can lead to cellular necrosis and further recruitment of monocytes and lymphocytes, with a concomitant release of cytokines, growth factors, and proteolytic enzymes. This can set the stage for local necrosis within the lesion and its autocalytic expansion. The so-called fibrous plaque is formed. As the lesion enlarges, at some point, flow is impaired. In advanced fibrous plaques, the endothelium may fissure, particularly the thin margins of the fibrous cap, resulting in hemorrhage, thrombosis, and ischemia, which is the first endpoint that results in clinical ascertainment of the process that has been evolving over decades. Finally, as the thrombosis is expanded and circulation is stopped, acute occlusion of the arterial lumen takes place.